Yes, welcome to Module 5, Lesson 10, conducting a simulation to estimate the probability of an event. Okay, so a simulation, we will need to define that. A simulation is a situation where you employ some sort of tool or device, such as flipping a coin, rolling a number cube, picking a card, okay, to simulate something that might happen in the real world. So, for example, and we're going to see this in this lesson, is this idea of predicting the outcome of, whether a birth would be a boy or a girl. In that sense, flipping of a coin would be a good alternative, in that there's a heads or a tails, which it could be a boy or a girl. Okay, so that would be a simulation. Okay, and simulations, they're methods used, and they're actually used in industry and business and science that estimate probabilities that can be used for problems in which it might be difficult to collect data by experimentation, okay, or by developing theoretical probability models, okay. So if it's very difficult, maybe to collect this data by experimentation, they might want to go ahead and use a simulation. And of course, that may not involve, flipping a coin, but other possible simulations. For example, when companies are trying to approve maybe a new drug for cancer, they may use a model like a mouse, okay, a mouse model, in the sense that they use the mice to predict what the outcome might be on a human being. Of course, they can't be entirely sure, so therefore it is a model, and it's only a first line model, but it is in some terms a simulation of the real thing. Okay, so they need to get it done quickly. They could use lots of mice, where you might not be able to. Of course, you can't maybe round up a whole batch of people too quickly, and whereas mice you can. A bit more ethical, though some would disagree, to do testing on mice rather than humans. Okay, so anyway, yeah, simulations. So in this lesson, we're going to use things like coins and number cubes and cards to generate some outcomes that will represent real outcomes. Okay, and that's the whole idea of what a simulation is. It's using one thing to represent another. Okay, so the plan is to ease you into this idea of simulation. Okay, so let's go ahead and begin. All right, so in previous lessons, we have estimated probabilities of events by collecting data empirically, okay, and empirically, this term right here, we should really have a vocabulary list early on, huh? Empirically means by experiment, okay, just write that down here, by experiment, okay, so just remember that's what empirically means, all right? So yeah, you estimated probabilities of events by collecting data empirically or by experiment, or by establishing a theoretical probability model. Okay, remember our theoretical probability, what should or what might be expected to happen. Okay, there are real problems for which those methods may be difficult or not practical to use. Okay, so they may be difficult or they may just be not practical. Okay, simulation is a procedure that will allow you to answer questions about real problems by running experiments that closely resemble the real situation. Okay, and this idea of closely resemble, not exactly, okay, but closely resemble the real situation. All right, it is often important to know the probabilities of real life events that may not have known theoretical probabilities, because there are some real life events that they do not have known theoretical probabilities. There's no 1 out of 2, no 50-50 that goes along with this with these events. Okay, scientists, engineers, and mathematicians. Okay, everybody here together. This is our STEM. Our STEM people, STEM workers, STEM professionals. Hopefully, that'll be one or more of you one day. Science, engineers, and mathematicians design simulations to answer questions that involve topics such as diseases, which I had referred to before, diseases, water flow, climate change, and the functions of an engine. Okay, all kinds of things. I mean, this is just the tip of the iceberg as far as of what could be tested through simulations. Results from simulations are used to estimate probabilities. Okay, to estimate probabilities that help researchers understand problems. Okay, and provide possible solutions to these problems. Okay, yeah. All right. Well, I hope that is clear enough to you. The truth is, in real life, we want to make certain strides towards problem-solving steps or cures to certain diseases, and the only way to do that at the beginning sometimes is to use a simulation. Sometimes those simulations are even in a computer. There are scientists, engineers, computer programmers out there that enter data into a computer, and they run algorithms that they have created, which will help them decide whether it is a good idea to even begin sometimes further testing on some sort of device or some sort of new solution to a problem. Okay? All right, anyway, example 1 here starts to talk about families. Okay, and families, as you can imagine, have children. Okay? So, and we've seen this before. So example 1, how likely is it that a family with 3 children has all boys or all girls? Okay, and we talked about this theoretically in class. Let's assume that a child is equally likely to be a boy or girl. Okay, instead of observing the result of actual births, okay, a toss of a coin, a fair coin, could be used to simulate a birth. All right. If the toss results in a heads, and this is in this example, a heads, then we could say a boy was born. If the toss results in tails, then we could say a girl was born. Okay. If the coin is fair, okay, i.e. heads and tails are equally likely, okay, then getting a boy or a girl is equally likely. Okay. All right. So here's exercises 1 through 2. Suppose that a family has 3 children. Okay, 3 children. To simulate the genders of the 3 children, the coin or number cube or a card would need to be used 3 times, once for each child. Okay? For example, 3 tosses of the coin resulted in HHT, representing a family, 2 boys and 1 girl. Okay? Note that HTH and THH also represent that same scenario, okay? 2 boys and 1 girl. All right, so number 1. Suppose that when a prime number is rolled on a number cube, it simulates a boy birth, and a non-prime number simulates a girl birth. Okay? So using such a number cube, list the outcomes that would simulate a boy birth and those that would simulate a girl birth. Okay? So, what we need to know, of course, for this one, if you want to pause right now and go ahead and do that, because you may understand this idea of prime and non-prime. Okay? Prime numbers are very special versus non-prime numbers. Okay, so prime numbers would be, truly, 1 is not a prime number necessarily because it is a very special number in itself. Excuse me. But I'm going to put it here on the prime side. So prime number would be 1. Now 2, of course, is a prime number because it only has 1 and itself as factors. Okay, there's no other way to make 2. 3 is also a prime number. Okay, now 4, okay, is not a prime number because 4 can be made 4 times 1, 2 times 2, etc. 5 is a prime number. Okay, and then 6 is not a prime number because it can also be made with factors other than 1 and itself, such as 2 times 3. Okay, so what we're going to do here is we're actually going to take off take off 1 here, because I realized something. It wasn't saying prime versus composite. It was just saying prime versus non-prime. And 1 is a non-prime number, though it's not a composite number either. It is the identity number. Okay, so there we go. So if we look at that right away, we could probably answer this last question here. Are the boy and girl birth outcomes equally likely? In this case, with this number cube, we would say yes, because there are 3 out of 6 chances to get the prime numbers, okay, which would be a boy, and then a 3 out of 6 or 1 out of 2 chance to get a non-prime number, which would be a girl, okay. So they are equally likely. But what we haven't done is we haven't actually listed the different scenarios, okay, the different roles. So if you would go ahead and do that, maybe create a tree diagram, all right, and pause right now and come on back and let's see what you got. Okay, well, hopefully you didn't go too crazy with your tree diagram. I just started doing something here. I'm not sure why I asked you, but I'm thinking to do this. But first, like the first birth could be, okay, these 3 would be, those were non-prime, that would be a girl, and then these 3 would be non-prime, and that would be prime, and that would be a boy. Okay, and then you'd have to go, what if you rolled a 1, then you could either roll a 1, 4, 6, 2, 3, 5 off of that 1. I'm not sure. Yikes is the actual answer, but that's the answer. The answer is yikes. But anyway, yeah. So this would be equally likely, just like we had said before, because we have the 3 out of 6 possibility for a boy and 3 out of 6 possibility for a girl. The odds are, the chances are, the probability is equally likely that you would have a boy or a girl. So now we're going to look at a deck of cards. So number 2 asks, suppose that one card is drawn from a regular deck of cards. A red card, okay, simulates a boy birth. Okay, red card, boy, and then a black card simulates a girl. Okay, describe how a family of 3 could be simulated. Okay, so how could we simulate, just like we had done before? Remember, we had talked about with the coin. With the number cube, it was a prime number for a boy, non-prime number for a girl. How might we use these cards to simulate 3 children, a family of 3 children, and their birth order? Now, the key difference here, that when you have a card in a regular deck of cards, the key difference between that and, let's say, a coin or a number cube. So with a coin or a number cube, the thing is you have no need for replacement. Okay, so no need. You don't have to reset the entire coin or reset the entire cube, because the thing is, you take the cube, you roll it, you have your 1 out of 6 chance of rolling one or the other numbers. You pick that cube up again, you roll it again, and automatically it's the same 1 out of 6 chance. Coin, flip it, 1 out of 2 chance of heads or tails. Take it, flip it again, same thing. Okay, you don't need to do any. There's no such thing as replacement. Okay. Now with the key component here with the deck of cards is that you would want to have replacement. Okay, so it's going to be a matter of, they've already set up the parameters here. You know, it's if it's a red card, it's a boy. If it's a black card, it's a girl. So the only thing that would be different is that you need to replace cards. So you know, you pick once, pick a card, record result, okay, and then replace card, and then start over again, okay, and then maybe replace card and shuffle, okay, just to mix them up as well as you can, okay. So in this case, with the regular deck of cards and drawing from that, the only requirement here that would be different than the coin, of course, and the cube would be that you need to replace. Okay, you need to keep that probability the same always, because in a deck of cards, I'm not sure how many of you know this, but there are a regular deck of cards. There are 52 cards. Okay, 26 of which are red, and 26 of which are black. Okay, so you already have, it's the same with the prime number and the non-prime number, 3 out of 6 and 3 out of 6. This is 26 out of 52, which is the same chance, which is 1 out of 2. So far with the cube, the way we've created it was a 50-50 chance. The coin is just naturally 50-50, a fair coin, of course. And the deck of cards could also be made into a 50-50 chance by just saying, red versus blue. Okay? So yeah, just replacement there. And that's all that problem was getting at. Okay, so now example 2. Simulation provides an estimate for the probability that a family of 3 children would have 3 boys or 3 girls by performing 3 tosses of a fair coin many times. Okay, many times. Each sequence of 3 tosses is called a trial. Okay, so here's another word here. Each sequence of three tosses is called a trial. And why 3 tosses? Well, 3 tosses to simulate 3 children. Okay, so this idea of 3 children. All right, so that each one of those 3 tosses is going to be considered or looked at as being a trial. Okay, so if a trial, okay, just to hopefully understand that. So I flip. I'll just do right here. So I flip a coin. I have a heads. Flip a coin, tails. Flip a coin, heads. Okay, that is one trial. So this would be trial 1. We could even put it in a, so you put trial. Okay, here's 1. Then if I had trial 2, flip, tails, flip, heads, for example. That's trial 2. So here in this scenario here, H2H, I had 2 boys, 1 girl. Then I had 1 boy, 2 girls. Okay, in this trial. Okay, so each one of these is considered a trial. Okay, so hopefully that's as a little clearer than mud at least. Okay, all right. So if a trial results in either HHH or TTT, then the trial represents all boys or all girls. Okay, which is the event that we are interested in. Okay, so we are interested in these 2 events, the HHH and the TTT. Okay, all boys or all girls. So these trials, in this case, HHH or TTT, would be considered a successful trial. All right. If a trial results in any other order of H's and T's, then it is called a failure. Okay, so that is for this simulation in particular. This is very particular to this situation. We are trying to see the likelihood or the probability of all H's or all T's, so all boys or all girls. Okay, that is what we're shooting for. Whenever we get one of these, an HHH or a TTT, it would be considered a success. Okay, a successful trial. All right, and again, this could be applied to other situations in the real world, which is pretty much the big idea here. So the estimate for the probability that a family has either 3 boys or 3 girls based on a simulation is the number of successes divided by the number of trials. Okay, it's the number of successes divided by the number of trials. All right, estimate for the probability. Okay, so, and that is very much what we've been doing already. Okay, we've done this in the past. It's very, very similar. It's just that we've added some new terminology. Okay, this idea of successes. Okay, all right, and number of trials. So suppose 100 trials are performed, and that in those 100 trials, 28 resulted in either HHH or TTT. Then the estimated probability that a family of 3 children has either 3 boys or 3 girls would be 28, okay, which was the number of successes, all right, over 100, which was the number of trials, which of course equals 0.28 or 28%, okay? So that is the estimate of the probability that a family has either 3 boys or 3 girls. Now, that, of course, is not a theoretical probability, okay, because we've done that before, and the truth is, one or the other of those is probably even going to be a greater percentage. Okay, this is just based on observation. Okay, based on the flips of the coin. Okay, but anyway, just a new little formula to know. Okay, so in number 3 here, let's go ahead. I'm going to have you do this. Pause after I read this here. So find an estimate of the probability that a family has 3 children. A family with 3 children will have exactly 1 girl using the following outcomes of 50 trials of tossing a fair coin 3 times per trial. Okay? And of course we had, like we had before, H was a boy birth, T is a girl birth. Okay, now again, our goal here is exactly 1 girl. All right? So in this case, exactly 1 girl, any scenario or any trial that results in exactly 1 girl is going to be our success. Okay? Our success. So, and again, the number of trials here, as you can see, is 50 trials total. All right? So go ahead and pause and do that, and then come on back. Okay, and while this is not very difficult to do, the most important part, or the part that got me here, was I needed to look over these 50 trials very, very carefully, and I had missed 2 the first time through, and still had missed another 1, and then I got the final one. Ooh, man, it's kind of tough, these H's and T's, really confusing to look at. Anyway, after finally getting it, I forgot all that, sorry, there they were, okay? So I had, no, actually I need 1 more, there, 3 more, maybe 1 more, see that, I missed a few going through, so ended up with 16 successes, okay, and again, a successful trial, okay, and again, each one of these is a trial. A successful trial was the one that had 1 T only, 1 T and 2 H's, okay. Out of 50 trials, okay, because all of these, there's a total of 50 here, then we do the division, 8 over 25, which equals 0.32 or 32%, okay. So based on what you found here, would you consider it likely that a family with 3 children will have exactly 1 girl? From your own experiences, how many families do you know who have 3 children and exactly 1 girl? Well, my family has 3 children, exactly 1 boy, which was me. Trying to think of others that I know of. Yeah, I have another, my wife's sister's family, 2 girls, 1 boy. Okay, that would be the 1 boy, exactly 1 boy situation, which is not exactly one girl, which is what we're talking about here. But anyway, if you do remember this idea of likely, okay, likely, now 32% or 0.32 would not necessarily fall into the likely classification, because if you remember in that probability scale, I think right in the middle, that 50-50 point, okay, was where likely began, okay, and anything less than that was considered less likely, okay, and then, impossible is, of course, way down here with 0% chance, of course, but not necessarily likely in this simulation, okay? All right, so, yeah, let's move on to the next. Okay, so I'm going to ask you to go ahead this time and actually get a number cube. Most of us have number cubes somewhere in the house, and if you don't have a number cube, maybe you can make a spinner with the numbers 1, 2, 3, 4, 5, and 6 on it. Yeah, be creative. Just one way to you can, because it'd be really nice if you did do these trials yourself at home. I'm still considering whether or not to do these trials because it's going to take 150 rolls of a die. So yeah. Anyway, I would really highly recommend that you do this yourself. It's nice to see it happen on your own. Okay. But anyway, let's go ahead and look at this. And it says here, number 4, perform a simulation of 50 trials by rolling a fair number cube in order to find an estimate of the probability that a family with 3 will have exactly 1 girl. And probably the most important part of this problem, not necessarily all the rolls, okay, but just this idea too of how you set this up, okay? So firstly, you need to specify what outcomes of one roll of a fair number cube will represent a boy and what outcomes will represent a girl, okay? So why don't you go ahead and just think of that, just consider it. You can just throw it down there and come on back and we can talk about it. How would you work that out? Okay, so I'm not sure what you did. Hopefully you just kept it simple. And before, we had ways to get a boy, ways to get a girl. The first way we saw in the example prior was, a boy would be any prime number, which were 2, 3, and 5, and then the non-primes 1, 4, and 6 for a girl. Okay, you could do 1, 2, 3 would be a boy, 4, 5, 6 would mean a girl, or you could do 4, 5, 6 was a boy, 1, 2, 3 is a girl. Okay, you couldn't do even numbers and odd numbers because we only have. Well, we could do that. We could do even and odd. I'm sorry. Why did I not think that? Duh. Yeah, you could do even and odd. Okay, even and odd, which would be 1, 3, and 5 versus 2, 4, and 6. Okay, so either way, yeah. So the first thing you need to specify what outcomes. The most important thing is that your outcome always is going to need to be, your probability is always going to have to be 0.5 for either one. Okay, it has to be an equally fair roll. Okay, that's the only thing that matters in this case. Okay, because we have one of 2 outcomes, a boy or a girl. All right. Okay, so in B here it says go ahead and simulate those 50 trials. Okay. Keeping in mind that one trial requires 3 rolls of the number cube. List those results, okay? And I don't know exactly what I'm not looking right at your binder right now. I'm not sure exactly what it looks like, but you're probably going to need more room than what I see on my page here. So go ahead and grab another piece of paper. Highly recommend to go ahead and do it. So, and again, you could take a look at some of the problems in the binder. That one up there with the flipping of tossing of the fair coin in exercise 3, but before this one, just list them like that. So for example, if I'm rolling a coin and I'm going to use how about odd and even? I'm going to say boy odd, girl even. Okay, and let's say I rolled and I don't have a die in front of me right now. Maybe I'll go grab one. But let's say I rolled a 1 and then a 4 and then a 6. Okay, and I can put the commas or not put the commas. I don't care. 1, 4, 6. So what I notice here is I have 2 girls and 1 boy. Okay, 2 girls and 1 boy. All right. Now I am looking for exactly 1 girl as my success. So that wouldn't be a success, but it would be a trial. Okay, that serves as 1 trial. There's my 1 trial. I have 49 more to go. Okay, so 50 trials. Again, the larger the trial size, the more accurate your data tends to be. No guarantee, but it tends to be more accurate. Okay, so go ahead and do that. Grab a number cube, get a spinner, and go ahead and work that out and calculate your estimated probability based on your data that you collect, and just come on back and we'll just discuss it as well as we can. Okay, so we're back, and I did not do the rolls. I'm sorry. I looked around frantically for a die here in the room I'm in. I'm just hiding away somewhere quiet on campus so I could do this, and could not find a die. So anyway, just the big idea here is you did your 50 trials and you listed them out, okay, and then when it came time to calculate your estimated probability, you just went ahead and took your number of successes, okay, and again, in this case, your successes were going to be anything that had 1 girl in it, okay. So in my case, I was doing boy odd, girl even, possible scenarios for me that would have yielded that. This would be my possible scenarios here would have been like 2, 3, 5. This example would have been 4, 4, 3, 5. Okay, will be another one. 6, 3, 5. Okay, getting the idea. And there would have been several more. Okay, several more possibilities. But anything like this would have been recognized as a success. Okay, because I had my one even number in all of these trials. Okay, those would have been successes, and let's say I had 25 of those. Okay, and I would have divided that by the number of trials. In this case, you were told to, or asked to, or encouraged to do 50 trials. All right, so that would have been my fractional probability, and that, of course, looks like this as a decimal, or like this as a percentage, okay? All right, but in that case, that's how I would have calculated my estimated probability again, and you would do the same, number of successes over number of trials, okay? All right, so let's move on. Oh, I was going to do another page there, okay. So now number 5 is now bringing us back to our theoretical probability. Okay, so let's go ahead and calculate a theoretical probability that a family with 3 children will have exactly 1 girl. Okay, so what I want you to do, and again I want you to pause, I want you to go ahead and do A and B. This is something we have done in the past. Okay, I want you to, if you need to grapple or persevere, please do, okay, and come back successful, and if not, hopefully I could point you into the path of greater understanding, okay? So go ahead and do A and B, and come on back. Okay, I'm going to go over this first part first, list all the possible outcomes for the family with 3 children, because I saw it as a great tree diagram opportunity, and hopefully you took advantage of it and did it with a tree diagram. You might not have, I understand, but I would like you to take the opportunity to use these tools when you have the opportunity. So here we go. So I went ahead and made my tree diagram. Okay, first birth could be boy or girl. Second birth, we continue our tree on, boy, 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 girl, or girl, boy, girl, girl. And then third, of course, we just extend our branches out, branch off of each boy and girl with another boy-girl scenario, and there we go. And now all I have to do is go ahead and follow my branches, BBB, BBG, BGB, BGG, GBB, GBG, GGB, and GGG. Okay, and there you can see we have 8 different possibilities. You may have remembered this, and maybe you actually peeked back in your binder, because yes, we have done this before, and there are 8 different possibilities there, 8 different possible outcomes for a family with 3 children. Okay, so I'm going to go ahead and erase all this and come on back. Okay, so now let's go ahead and assume that having a boy and girl are equally likely. Okay, calculate the theoretical probability that a family with 3 children will have exactly 1 girl. Okay, the theoretical probability that you will have exactly 1 girl. Okay, now we need to look at what those successful scenarios are. Okay, and yeah, well, go ahead, you do that, and maybe you have done that already. You probably have, because I asked you to, so let's just go ahead and do it. Yeah, so the first thing we need to do, exactly 1 girl, what are those successful trials, quote-unquote trials? There's 1, there's 2, there's 3, okay? So there are 3. There are 3 different trials, 3 different trials out of the 8 that will yield us success, quote-unquote, okay? Now, there are a few different ways. I mean, since they're all equally likely, okay, equally likely, we could just use this 3 out of 8 and just turn it into a decimal, 0.375, okay? That would be our theoretical probability. Oh, sorry, I forgot the 5 there. 375. Okay, that would be our theoretical probability. And we could also look at it differently. They are equally likely, but the truth is, each time you have a boy or a girl, remember your probability there was 0.5 each time. So if we had 0.5, we could just go ahead and multiply that by 0.5. Okay, and then multiplied by 0.5. And remember what we got. We got 0.375. Okay, so, I'm sorry, no, this was 0.125. Okay, so each one of these, remember each one of these here, the successful trials, as we say, each one of those, the probability of those occurring was this, right? Remember 0.125? And if we want to do either one of these would be okay. So we could have this one, or this one, or this one. And remember, when we're doing our or, the word or, when we're talking about probabilities, is going to mean addition. So therefore, we would just add 0.125 plus 0.125 plus 0.125, and we would come up with, of course, that number. 0.375. Okay, 0.375. So either way you look at it or calculate it, yeah, the probability, theoretical probability of having exactly 1 girl would be 0.375. And now the last part here, part C, asks you to compare the estimated probabilities found in your A and B above, in your number 4. Okay, so what did you find out? What was your result? How does this compare to the results that you came up with? Okay, and that'd be really, really interesting when you rolled your dice, rolled your number cube, what you came up with. So if it was anywhere near this, that is very good sign. If you're very, very far off, okay, if you got the probability, estimated probability, with your number cube of 0.75 something, whatever, 0.75, then you probably need to conduct more trials. Okay, so it's always good to have a theoretical probability that it can be used to compare to. Okay, but that's not always the case. Okay, example 3, basketball player. Okay, suppose that on average a basketball player makes about 3 out of every 4 foul shots. That seems like a pretty decent or fair estimate. In other words, she has a 75% chance of making each foul shot she takes. Since a coin produces equally likely outcomes, it could not be used in the simulation for this problem. We could not use a coin. Couldn't use heads versus tails because that's 50-50. We need a simulation that is going to help us give an estimate probability of some 3 out of every 4 foul shot situation. So instead, a number cube could be used by specifying that the numbers 1, 2, or 3 represent a hit. Foul shots. 1, 2, 3 every presents a hit or a successful foul shot. The number 4 represents a miss, and the numbers 5 and 6 would be ignored. Okay, that's kind of weird. But anyway, based on the following 50 trials of rolling a fair number cube, find an estimate of the probability that she makes 5 or 6 of the 6 foul shots she takes. 5 or 6 of the 6 foul shots she takes. Okay. So you can see first off what they've done here. So you have the possibility, you're rolling a fair number cube, right? You have 1, 2, 3, 4, 5, 6. These are your possibilities, your sample space, right? This is your possibilities here. So what they've done is they pretty much just decided to ignore these two, okay, take them out of the mix, okay? And so if you rolled a 5 or a 6, you just re-roll, okay? Re-roll. And they're saying that 1, 2, 3, these are good. These are shots that are made. And then a 4 is a shot that is missed, okay? So it works like that. So therefore you have the 3 out of 4 chance or likelihood, which is, of course, 75%, all right? So that's what they've done here. So they've taken this coin, and it just becomes more tedious, actually, because you're going to have to roll a lot more, because I'm sure you're going to roll lots of 5s and 6s, but you're going to have to ignore them, okay? But anyway, it looks like they have accumulated some data for us here, okay? And what they want us to do is now, based on the following, these 50 trials that they've accumulated, okay, find the estimated probability that she makes 5 or 6 of the 6 foul shots she takes, okay? So we've ignored the 75%. The 75% here was just helped us decide on how to how to set up our cube scenario. What was going to be a shot made, what was going to be a shot missed, okay? So that's all that was about. But now we want to know the probability of her making 5 or 6 of the 6 foul shots she takes, okay? So go ahead and look at this data and come on back after you have found that estimate of that probability. Okay? Okay, so let's go ahead and take a look at this. Now, the successes, this makes 5 or 6 of her foul shots she takes. Of course, you can't have more than 1 4 in a trial. Okay, 1 4. So I just kept looking. As soon as I saw 2 4s, I just moved on. Okay, if I saw no 4s, of course, I highlighted it. But so here's what I came up with. Okay, and I actually found them all on the first go. Okay, I looked and I actually did it on the first go, unlike before where I messed up a couple times. Anyway, we had 27 successes here. Of course, out of the 50 trials, which yielded a probability of 0.54. okay, or 54% chance of, of hitting 5 or 6 of the foul shots she takes, okay? Now, they have a little, in the teacher's notes here, they have a little aside about the theoretical probability of calculating this. And again, it's a little bit complicated just because there are so many shots. We're talking about 6 shots in a row. But anyway, if you calculate this theoretical probability out, you get about 0.5339. Okay, so the theoretical probability of this actually happening is actually quite high, based on this 75% free throw percentage. Okay? Anywho, yeah, so hopefully you got that, 0.54 or 54%, and we're successful with that. Okay, so let's go ahead and close here. In previous lessons, you estimated probabilities by collecting data and found theoretical probabilities by creating a model. In this lesson, you used simulation to estimate probabilities in real problems, and in situations for which empirical and theoretical procedures are not easily calculated. Well, it's not exactly what you did, but we did talk about this idea of simulation, which is really important. And we had to design simulations. We had to design, how are we going to use a 6-sided cube to simulate, hits or misses with at a free throw line. Okay. Now I understand what the hit is. Hit baskets. Okay, I'm sorry. I always think of hits as baseball. Anyway, that's besides the point. That's my problem, not yours. Okay, so simulation is a method that uses an artificial process, okay, like we did, tossing a coin or rolling a number cube, to represent the outcomes of a real process that provides information about the probability of the events. Okay, if we have an idea of the probability of an event occurring, we could use some artificial means to, and again, like I said before, early on, computer simulations are used more and more. Okay, we feed data into computers, and these computers have a quote-unquote, memory that is built into them, and they can understand. They know how to design these probability calculations. Okay, when I say know, they know because we allow them to know. Anyway, in several cases, simulations are needed to both understand the process as well as provide estimated probabilities. Okay, and simulations a big part of the real world that most of us don't have much to do with, but hopefully some of you would like to be part of this and really ride on that STEM locomotive, okay? And that is science, technology, engineering, and mathematics, okay? It is a great career choice, a very productive career choice, and hopefully some of you will find your way into it. Okay, thanks for watching, and see you next lesson.